Hello, everybody. We are very interested to introduce the new technology, create a new 3D printer for metal, which is different from the normal traditional 3D printer, depends on the laser. Dr. Dennis Moder, she is the head of application engineering, will introduce for all of us this innovative technology.
Thank you very much. Yes, so I will focus today a little bit on the technology as well as the application for patient-specific brackets, which can be also taken for, let's say, more classic or batch brackets, but also go a little bit more into some implants at the end to show you a little bit what we can do in the dental field. Yes, so first of all, who is Incus? Incus is an Austrian company founded in 2019. I had the pleasure to join the company in 2020 already and see the growth over the years, getting an innovative technology that was already great and impressive from the beginning to what we can reach and achieve now, which goes even further and better than what we could do before. Our company is the only provider for the technology that we call lithography-based metal manufacturing, in short LMM, and we provide really all the technology from the material to cleaning the parts. Then we have our partners that have all the knowledge on the debinding and sintering steps that come after the actual printing. We have already over 25 machines sold worldwide, a team of slightly less than 30 people with more than 20 different nationalities, so really getting the best of the people worldwide to make this technology even better. And we have really great investors that believe in our technology and are behind to help us make the technology better and better. About the process itself, we are a process based on light, so not lasers where we will melt the powder and so on, but light in terms of what you might know from SLA, so stereolithography. So we have a DLP projector that is projecting the whole image for one layer, and is polymerizing, so creating the 3D network of the plastic material where we have homogeneously mixed in the powder that we will want to have. So if we are talking brackets, it's usually 17.4 pH, or if we go into implants, we might be more in titanium 6.4. So basically our material, we have the storage of the material, so the raw material on the left side here, which is solid at room temperature, but liquefies with a heated blade that you can see on top. I hope everyone can see my mouse. So this blade is heated up, will pick up a small layer of the material, the raw material, spread it onto the build area where we have the projector projecting the image. Then the material solidifies around, and we can start with the next layer of material and project the next image. So the fact that the material solidifies again after each layer allows us to not need any support structures, so we can really freely print any part with overhangs just like that. Finally, we have also a really good green part at the end that has a nice strength. So for those who know binder jetting is a great technology as well, but the green parts and the depowdering can be a little bit messy. Well, we already have the powder mixed in the binder system, so we don't really need to deal during the printing process with loose powders and also not with the cleaning, which makes it a really clean process and quite safe process. So here's a little video of the printing. So there's the blade with the heated blade that is spreading the material that is kind of viscous, the projector projecting the image, and we continue layer by layer. So we can really process all the materials that are also possible to debind and sinter. I hope some of you know metal injection molding, so it's really the same principle. Yeah, so also the powders that are not possible to spread, which is necessary for all the laser-based systems. So here it is not an issue because we can adapt our plastic resin, so the resin that will react with the light, in a way that we can process that material. So what we get after the printing is this block where all the parts that we printed are stuck inside, and there's nothing easier than the next process to remove those parts. So this is what we call the decaking. We just blow hot air on the material and melt everything off that has not reacted with the light. All the material that is then collected underneath, in this case a glass Tupperware, we can just take it and reuse it for next prints. So there is no loss of material, and yeah, that makes everything nicer. Also, I don't know if you can see properly, but here we have a double gear which is placed above another double gear, so it's no issue to just print parts one on top of each other. They will just separate at the end. After that, sorry, after the process of the decaking, we will need to clean a little bit the parts because there's some material still on it, but this is possible with an ultrasonic bath in a cleaning solution that is really the minimum of the work. So what you can see here on the slide is our Hammer Lab 35 that will actually be replaced next year with the Hammer Evo 35 that we showed this year for the first time at the Formnext in November 24. The size of the build area is the same for the Evo in the lab. So we have a platform of 56 times roughly 90 millimeters in X and Y, and we can go up to 120. The pixel size that we have here is 35 micron. However, with the Evo, there will be some possibilities to even reduce the pixel size without losing the size of the platform, of the build area. To stay in the advantages that we have with this technology, we have a high resolution with the pixels. We also use small powders like they are using in metal injection molding, so usually a D90 of -25 micron. It's even possible to go even lower or to go a little bit higher, but we try to stay underneath the 35 micron of the pixels because this is where we show the best advantages. Also with the layer height, we try to go as low as possible for the quality of the part and for the surface of the part, but we also try to not be too low because we also want a good productivity. So we are usually with layer heights between 25 and 30 micron. But as you can see, it is possible to change the layer height from 10 to 100 micron. So just to see a little bit the economics of some brackets here. So the brackets have a height of roughly 3.5 millimeters. It is possible to place 238 parts in one layer. So we don't even talk about the stacking of the parts, which gives you an annual capacity of over 850,000 parts yearly, coming down to a print cost of 8 euro cents per part. So this is for the smaller machine. And then if we go to the upscaling, because we want to show that our machine is not limited to the small platform, we are capable of putting it to the next level, getting it to a production type. So we built our Hammer Pro 40, which is 2 scrolling projectors. So the projector is scrolling the image throughout the platform that is 200 millimeter wide. We have 2 projectors in parallel. So 2 times a 200 millimeters times 77 millimeters in Y that print at the same time. The printing speed is the same in terms of layers per minute, but we can, but in terms of productivity, we are much higher, and you will see it in the next slide. The rest of the machine, the principle is exactly the same than the lab machine. So if we go here to the productivity and the capacity of this machine, we have 2,000 parts per layer. So you can see the 2 platforms that are parallel to each other. 2,000 parts per layer, getting us a print cost per part down to 2 cents, 2 cents per part, and an annual capacity of over 7 million parts yearly. In terms of productivity, people who used to say a few years ago that we are not good enough in terms of capacity and print speed, now with the Pro 40, we can show them that it is definitely worth it to invest in the technology, to build parts that you spend much more money with machining or post-processing. If we talk about laser-based systems, the post-processing takes a lot of time. While here we always get really good feedback from polishing companies, really reducing the time and the effort that you need to put on it. Just to show also a little bit from what you get from powder bed fusion in terms of feature size and the how exact the details are. We are here around 100 and 140 micron for the minimum feature size, because this is like the laser melting the material at that spot. And we are talking about 35 micron pixel sizes. So we can really go detailed, and we can go down to plus minus 20 micron when it goes to the precision of the part, which is definitely not possible in powder bed fusion. Why would it be good? I think I've mentioned most of those points, why the patient-specific brackets are great by using LMM. We have the surface aesthetic of our parts that is less than 2 micron for the array. It's as close to metal injection molding as you can get. The repeatability is great. No support structures, a really low amount of polishing or manual rework, and a really easy really easy technology to process. Clean, easy, fast to learn and to use. The mechanical properties for all the materials, here's just the example of 316L, but all of our materials, when we say we have the material, we can get the same mechanical properties that the material should have. It's not just we can print it and that's it. No, we know also how to debind and sinter. So doing the heat treatment after the printing, to result to the right properties that the metal should have. Here's a small video of the journey of a bracket going through LMM. So first of all, it would be placing the material, the raw material in the printer, starting the print job. You can see there's a little screen where you can see what you are printing. then the machine does its job. We go through the process that we call decaking, and then it shows just putting it in the ultrasonic bath, couple of minutes, getting them out, and the parts are clean. Then it goes to the sinter furnace, so the heat treatment for brackets that are relatively small parts. It's also a process that can be adapted depending on the size that you have and make it even more economic. And then we have the little brackets. So that was really a nice video to do to show what we are capable to do. In terms of porosities of the part, we reach densities above 95% of the theoretical density. We usually more around 98%. And we don't have any porosities on the outside of the part. So we had the possibility to do a 3D scan with the synchrotron, and it just confirmed that we have a defect-free part. Here an example of a little bit older polished parts. Since then, we worked with more polishing companies, have the right contacts to give exactly what you need to have. So you can see it gets really shiny. Nowadays, we really have parts that go up to almost a mirror polished. Our customers are really satisfied with the work that we can do with our technology and the different polishing technologies. So this is basically a repeat of before. Sorry for that. It's possible to automate the whole process. We are working on upscaling every step of the process, from mixing the material to cleaning to everything. And really makes it a satisfying thing to do. I had the opportunity this year to do some depowdering on a binder jetting part, which is a little bit more difficult to work with because the powder is blowing in all the areas. You don't really feel that safe. We can really have a process that is nice and neat. So I mentioned a little bit titanium. So we worked a lot with titanium in the last 2 years to really get the closest possible to the medical grade titanium. We know it's really important in the medical field, whether it's the dental field or more operation field. We already have all the mechanical properties that are necessary for the material. There are still small adjustments that we need to do in terms of the chemical composition for the material, but it is planned to have it sorted out by the end of 2025. And when I say the small adjustment, we are talking about a carbon content that has a 0.05% too high of what had been decided a long time ago by the medical field. So we know that if you would go through the small additional steps to get it approved, to get the implants in, you will get all the requirements needed. So to summarize it all, we can do really complex green parts in MIM size range. The smallest part that we actually printed was 13 milligrams. Well, here in the slide, we are mentioning 1 to 200 grams components. It's a high advantage to not need any support structures for the printing, which reduces any manual labor to remove the supports, which I guess most of you watching this video usually have to deal with. We have really high green part strength, so we can use automation robots to transfer parts. This is not included in our company, but it's something that our customers can include. We have the highest resolution and surfaces that you can get in metal additive manufacturing. There's only one company that I know can reach similar parts, but in terms of productivity and scale up, they are not up to our level. And it's possible to really work with a wide range of materials as long as there is the possibility to debind and sinter, or to do any infiltration process. We worked with heavy alloys, heavy tungsten alloys. We worked with diamond composites. We worked, what was a really good example for the safe and simple production process is printing with precious metals. We don't lose anything with the powder flowing around, so we can really just use it in the printer and make sure to recover all the material necessary. And yeah, a really good feedback is really the safe working environment, something that we are used to here in the company, but hearing the feedback from our customers always saying that it is much nicer, much neater, and safe than most other processes. And that's it. Thank you very much.